You ever see a quarterback launch a perfect spiral or an outfielder unleash a laser beam to home plate and just think, how on earth do they do that? Well, the secret isn't just raw strength, it's physics. Today, we're going to break down the real science behind the perfect throw, starting with the simple, clean rules we all learn in school, and then we're going to see what happens when that simple science collides with the messy, real world.
So let's get right to it. What is the perfect angle to hurl something if you want it to go as far as possible? Now, if you took a high school physics class, you're probably screaming an answer at the screen right now. And you know what? You'd be right, but you'd also be kind of wrong. Let's dig into why. All right, to figure this out, we have to start where all good physics problems begin, in a perfect, simplified world. A world with no messy complications and, most importantly, no air.
In this perfect little bubble, when you throw something, its path is this beautiful symmetrical arc called a parabola. Just look at it. The first half of its flight is a perfect mirror image of the second half. It's so clean, so predictable, all thanks to one single constant force, gravity.
Now, to understand this, physicists do something really clever. They break the motion down into two separate parts that are happening at the same time. You've got the horizontal part, where the object is just cruising along at a steady speed, and then you've got the vertical part, where it's in this constant battle with gravity, slowing down on the way up, stopping for an instant at the top, and then speeding up on the way down. When you look at it this way, the whole problem gets way easier to solve. So, the key term for our question is something called range. In physics speak, that's just the total horizontal distance the object covers from start to finish. Our mission, then, is to figure out which launch angle makes this range the absolute longest.
And this, my friends, brings us to the big reveal. The secret that's been hiding inside the math of that perfect parabola this whole time. Let's go find that optimal angle.
This is it. This is the key that unlocks the whole thing, the range equation. It might look a little intimidating, but it's pretty simple. It just tells us that the range, that's R, depends on three things: how fast you throw it, the constant pull of gravity, and the one we really care about, the launch angle theta. So how do we find the sweet spot? Well, that equation has a sine function in it, and that's the part that changes with the angle. As this quote explains, if we want to make the range as big as possible, we need to make that sine part as big as possible. And the absolute biggest value of the sine of any angle can ever be is 1. So let's solve it. It's actually super easy. We just need to make that sine of 2 times the angle part equal to 1. Well, what angle has a sine of 1? 90 degrees. So if 2 times our launch angle has to equal 90, we just divide by 2 and we get our magic number. 45 degrees. There it is. In a perfect world, this is the answer, the golden angle. You launch any object at exactly 45 degrees and it will travel the farthest possible distance. A beautifully simple answer from a beautifully simple model. Case closed, right? Well, not so fast. Because if you've ever actually tried this or watched professional athletes, you know something's off. A javelin thrower, a shot putter, a golfer hitting a drive, none of them launch at exactly 45 degrees. Our perfect little model, it's missing something. Something big. And that missing ingredient, the villain that comes in and messes up our perfect story, is air resistance. You might also know it as drag. It's the one force our simple model totally ignored, and believe me, it changes everything.
Now, for something moving fast, like a baseball, we're not dealing with just any drag. We're dealing with quadratic drag. It sounds fancy, but the idea is simple and kind of terrifying. It means that as the object goes faster, the air pushes back way harder. If you double your speed, you don't just get double the drag, you get 4 times the drag. It's a powerful force, and it's always pushing directly against the direction the object is trying to go. So this just completely wrecks our simple little model. Unlike gravity, which is steady and predictable, drag is constantly changing because the object's speed is always changing. It fights the object's motion both horizontally and vertically. And what does that do? It warps our perfect symmetrical parabola into something lopsided. It gets so messy, in fact, that you can't solve it with simple equations anymore. You usually need a computer to figure it out. So what does this lopsided, skewed, real-world path actually look like? Let's take a look at the asymmetrical truth of throwing something here on planet Earth. This quote from a research paper just nails it. Because of drag, the object is constantly losing horizontal speed. Think about that. It means the second half of the flight, the journey down, is going to cover less ground than the first half. The peak of the arc is no longer in the middle. It gets shifted forward, closer to where the object is going to land. And here's the proof. Check out this hard data from that same paper. They modeled a baseball thrown at our so-called perfect 45-degree angle. You can see drag reduces the height and the range, no surprise there. But look closely at that last row. That's the real smoking gun, the impact angle.
Get this. The ball was launched at 45 degrees, but it hits the ground at almost 59 degrees. It comes down way steeper than it went up. That is the signature of air resistance at work. The beautiful, elegant symmetry of our parabola, it's gone. Broken.
Okay, time for the main event. Let's put these two worlds, the ideal physics class world and the messy real world, side by side to really see what's going on.
And this comparison just says it all, doesn't it? On the left, you've got that beautiful, clean parabola, shaped only by the constant pull of gravity. But on the right, that's reality. A path that's constantly being warped by two competing forces. Gravity, always pulling straight down, and drag, always pushing back against the object's motion. So here's the final scorecard. In our perfect world, we get a symmetrical parabola, and the best angle for max distance is 45 degrees. But in the real world, with air drag, we get a lopsided, asymmetrical path. Our height and range are both smaller, the flight time is actually shorter, and this is the big one, the angle for maximum range is now less than 45 degrees. Why? Because you want to get the ball downfield, but spend less time high up in the air fighting all that drag.
Now, does this mean your high school physics teacher lied to you? Absolutely not. The 45-degree rule is a fantastic approximation. It's a great tool for thinking about the basics. But the real lesson here, the deeper lesson, is that understanding why and where a model breaks down is just as important as understanding the model itself. Knowing the limits of our knowledge, that's where the true understanding really begins.
And that really brings us to the big takeaway. The perfect parabola is a useful simplification, a simple model we use to understand a complex reality. We do this all the time, right? In physics, in economics, even in our own daily lives. So the question I want to leave you with is this. What other perfect parabolas are shaping the way you see the world? And what real-world air resistance might you be ignoring?